Let's learn to code the diffusion transformer. So diffusion model can play a crucial role towards superintelligence because we can train both text and images with diffusion, and we can make it a lot more merged than training transformer token text autoregressively and then diffusion just images with diffusion. We will learn about this transformer latent diffusion GitHub repository. So it has these files: denoiser, diffusion, train, and transformer block. And these denoiser and diffusion, they are based on transformer architecture and not UNet architecture. Just to add quickly, we will be understanding the code and logic and mathematics. We will not be training it in this video. We will be training it in future videos, but now we will just understand code and theory. It's shown in the paper Diffusion Transformer that transformer diffusion scales better than UNet diffusion. Core components of this repository: denoiser. So this is the file, a transformer-based network that learns to denoise images in latent space. Input: noisy image latents, noise level, and clip encoded text embeddings. This might be replaced later, but let's learn it with this now. Output: clean latent predicted by the network. Then we have diffusion generator module. Handles image sampling, reverse diffusion using the denoiser. So this is just using this denoiser. Supports DRN solvers ++, fast generation, and classifier-free guidance. So this is just for generation in this text. Classifier-free guidance, I think it means no text or yes text, I'm not sure. So you can prompt it or without prompt, I'm not sure. So it works by training the model to handle both conditional and unconditional inputs, allowing it to generate samples based on a desired condition like text prompt or without any specific condition. And then this diffusion transformer class or file wraps everything, loads pre-trained models if you, denoiser, variational autoencoder clip, provides text to image generation, generate image from text. So we will try to understand and code everything from scratch. So I'm not sure, I guess clip we don't code from scratch, but variational autoencoder and denoiser, we have denoiser here. I don't know about this one, we'll see. But I think with this project we will understand how to do diffusion transformer from scratch. Then we have these architecture details. So sinusoidal embeddings encodes the scalar noise level into a high dimensional representation using sine, cosine, positional encodings. So this is the trick. Instead of passing time step, so time step is connected to how much noise there is in the image. In the beginning time step there is no or little noise, and in the ending time steps there is a lot of noise. So diffusion model needs to have the time step to know how much noise there is and how much noise it should predict to remove. But they don't just pass in the number, time step as a number from 0 to 1000, whatever. They actually pass it in this format, in a sinus wave format, or actually just a few numbers. So they have this constant, it's always the same. So they have these numbers here, sinus of these numbers and cosinus of these same numbers. And I don't know if this is example or that by ChatGPT or the real example from Cole, but it doesn't matter. So this constant, and then depending on the time step, you just multiply each of the numbers with the time step. So 6 times 2 or 6 times 3. And now you will pass in these values. So you will calculate sine of each of these. So instead of passing in 3 as the number, you pass in these values when you calculate sine. So you pass in the wave, or I guess a few points on the sine wave and a few points on the cosine wave. So I think that even just giving the scalar value would work, but maybe this sine cosine works better. So because LLM needs to learn, when you give it 3, it needs to learn, okay, it's close to number 2, but it's far from number 30. So it's close to step 2, but far from 30. It needs to learn that. So I'm guessing the sine cosine
kind of has more information, more points to compare, so maybe it will learn better, easier, faster. And this is important for linear, for these raw numbers. Hard for a network to distinguish patterns at different scales. For example, the difference between 1 and 1.1 might matter a lot, but between 100 and 100.1, not so much. Then we got self-attention. Token interacts with itself, denoising structure. Cross-attention. Token attends to external condition, noise level, or text. So this is the step or text. MLP-SConv. MLP with spatial inductive bias via depth-wise convolutions. We will see what this is. Then we have this decoder block. So we have our input pass through layer norm, pass through self-attention with residual connection. Then we got layer norm the input and conditioning in cross-attention and residual, and then the MLP and residual. So we process our X, but we also add the raw X, so this will learn to preserve some data. So basically this processing step, this will evolve such that later it will just complement this raw data, and it will be good in the end. So this is some information that's important that needs to get passed directly without being processed, and this will learn to complement it. Then we have DenoiseTransformer block, encodes the image into patches plus position embeddings, then passes through n transformer decoder blocks. It's the next day morning, so let's continue. Forward process image generation. In diffusion generator.generate, initialize noise image xt. So iterative denoising, predict clean latent x0 prediction, update xt using ddim or dpm solver++. Then final latent is decoded by the variational autoencoder decoder. The key part here is x0 prediction. The clean image is denoiser, giving it xt, noise level, and level.
Let's code it from scratch. So I will create a new file, transformer block.py. Let's see what this linspace does. So if I print torch linspace 1 to 10, we go 1 to 10 with 5 steps in between, equal steps in between. Then let's see torch log and torch exp. So we have this tensor 1, 10, and 100. So what torch log will do, you see these numbers 0, 2.3, 4.6. So e to 0 is gonna be 1. So torch log will find which number. When you say e to this number, you get this number. So it will find logarithm, natural logarithm of this number. So e to 0 is 1, e is Euler's number, 2.7 something. And then e to 2.3 is 10, and e to 4.6 is 100. So it will just find natural logarithm of x. And then exp is reverse of log. So you will just put e to these logs. So you see exp of log of x. So if you do this, you will just get the same, because those are two reversing operations that get the same result in the end. So exp of log, so you will put this e to 0 is 1, e to this is 10, e to this is 100. Now we are trying to understand this line of code in this sinusoidal embeddings. So when it calculates frequencies with torch exp, torch linspace, torch log, and this stuff. So we are trying to understand this line. So we want frequencies to grow exponentially. For example, 1, 2, 4, 8, 16, 32, etc. but linspace gives linear steps. So we take log of A and log of B. So those are starting and ending points in the linspace, A and B. From where to where does linspace go? Make linear steps between them, and then apply exponential to get exponential steps again. Let's see on an example how that works. So we want to make 6 different numbers between 1 and 1000, but we don't want them to be linearly spaced. We want them to be exponentially spaced. So this is the result that we want. You see here, this is 1, this is 3.9, this is 15, this is 63. Because of this means this number times 10 to 1. So this is 63, this is 251, this is 1000. Because it's 1 times 10 to power of 3. So it's growing exponentially, so that's what we want. Okay. So we take linspace from log of A to log of B. So from log of 1 to log of 1000. So that's gonna be 0, log of 1 is 0, to log of 1000 is 6.9. And we take 6 steps. And now we just exponentiate them, exponentiate these. So we get back our from 1 to 1000. And it's exponentially growing exponentially because we are literally using this linear space as exponents to the exponential function. So that's why it's growing exponentially. So let's summarize again. We want to create 6 numbers between this range, but they should grow exponentially. So instead of using linspace to calculate the numbers, we use linspace to calculate the exponents. So they grow exponentially later. So to calculate exponents, we don't calculate them from 1 to 1000, we calculate them from 0. So we just calculate exponents. So the first exponent should get us this one. The last exponent, e to the last exponent, should get us 1000. So we actually just calculate exponents in this linspace. And when we use those exponents, e to the exponents, then we're gonna get exponential growth. And we're gonna get these exact numbers because we used log of them. That's why we will get, because we used log of them in the linspace. So that's why here in frequencies, we are doing the same thing. So first we have minimum frequency. So we take log of the minimum until log of the maximum, so the ending frequency, which is gonna be 1 to 1000 by default. And then we put it through linspace to create exponents, and then we exponentiate with those exponents. I also forgot to say that the amount of these exponents we create is embedding dimension divided by 2 with integer division. So we'll look further. So this would be our number 6. So for example, in our example, that would be our number 6 here, 6 exponents. So we'll see why embedding dimension divided by 2. But before we talk about embedding dims, let's just ignore this and consider this a number. Just look at, so let's see this full line. So we just have frequencies, torch exp, torch linspace. We have the same thing that I just explained, and if I do this, we get the same numbers. Now they are a bit, we have only 4 numbers here. So now linspace is gonna create 4 equally distanced exponents as opposed to 8. So these numbers in the middle will not be same, but these beginning and ending are 1 in 1000. So our exponentially growing array is 1, 21, 464, and 1. Oh, this is 10,000. Sorry, this is 10,000. So now we understand this, but let's understand the entire class. It's not that difficult. This was the main part, I think. You probably know this, but if you have some module and inherits from NN module, you define in itself, and then super to call this superclass, and we can print initialize here. So if I initialize my module, it's gonna say initialize because as I initialize here, as I create the instance of this class, it runs this initialize method. So whatever is in it, it's gonna run. So let's see how to save some values in register buffer. This is just our memory that we can save values. And these values would not be trained in a neural network. Those are just constant values that are saved for the use by the neural network. So we just have this register buffer, the name of the variable, and value. So if we initialize this class, this module, class also, and we can say m, so the name of the class module instance, dot some value to get this value. You can still use dot CUDA, to, or eval, etc. and the buffer moves along with the module, so you can put it to device, to GPU, to CPU, etc. So in the code, they are saving these angular speeds, so they are saving the frequencies, but not in this frequencies format, but they are converting it to angular speeds. So they're multiplying with pi and 2.0. Why multiply frequencies by 2 pi? This is to convert frequencies in hertz into angular frequencies in radians per second, which is necessary for computing sine and cosine waves correctly. So a sinusoid is typically written in terms of angular frequency omega. So sine of omega t is equal to sine of 2 pi frequency times t. So we are converting 2 pi frequency. We want to actually have it as this omega. So this is important to understand. When we have a frequency, some number, 1, what we want to give to the AI is that there is one full cycle of sine wave between 0 and 1. Or when frequency is 10, we want to give to the AI a sine wave that has 10 full cycles, 1, 2, 3, there is 10 of them, between 0 and 1. So this is the number of cycles, but this is the problem. If we need to convert the frequency itself does not have the full cycle. The blue line is the frequency. So we need to convert this frequency into this sine wave, into radians. So that's why we multiply by 2 pi. So maybe this should not be called frequency. This should maybe be called number of cycles. So you see, it just says between 0 and 1 there is one cycle. But we need to generate that one cycle, that sine wave with one cycle, by multiplying number of cycles with 2 pi. So when we multiply it with 2 pi, and then we take sine of that tensor, that's when we get this. But if we just take sine of this number of cycles, that doesn't mean anything. It's not correct. I will leave you a ChatGPT explanation link here. So basically, if we have this frequencies number, we need to make each number bigger by 2 pi. So when we take sine of it, the sine will be correct. The number of sine cycles will correspond to the frequency number, which should just be a number of cycles, not frequencies, whatever. Let's now understand this forward pass. So this is some setup. This is the same thing we did. We calculate frequencies, and then we calculate angular speeds by multiplying 2 pi times frequencies. So we get 1 to 1000, and then multiply that by 2 pi, we get these numbers. So 6000, 200, etc. So this means between 0 and 1, there will be 6283 full cycles, and a bit more than full, because there is a bit more here. So this is just the frequency we will pass into our neural network. Angular frequency, I should say. So in the forward pass, we get this x, which is a tensor. So let's say we have this tensor x, it's 0, 1, 2. So the shape is 3, 1. And then x times angular speeds. You see here, 0. Oh, yeah, it's all zeros. Then 1 times angular speeds, and then 2 times these 3 angular speeds here. So x is noise timestamp, noise level. So if x is 3, then noise has been added 3 times to the image. So now, instead of just passing this number 3 to the neural network, it's better if we convert that number 3 into sine wave, and then neural network will learn better, more. We'll be able to extract data better from it than just passing this scalar number. After we have these 3 tensors, x times angular speeds, then we will take sine values of these tensors and cosine values here and here and here and here and here and here. In order to show you, I just generated a lot more frequencies. So position 1, noise 0. So this is noise 0, noise 1, 2, 3. So these are noise time steps. This is what we can learn. If I told AI, if I have these frequencies of sine and cosine, is AI just gonna memorize to associate them with noise levels? So because we are pre-generating these, so this is gonna be always same frequency, like same for the 0th time step, always for every image. This is gonna be always same, always same. So they don't depend on the image, they just depend like on the time step of the noise, which is always the same, 0, 1, 2, 3 for every image. So I asked the AI if it's just gonna memorize these numbers, and then that's how it will know which timestamp it is. No, it's much more powerful than simple memorization. Here is the intuition. Sinusoidal embeddings encode continuous position information smoothly. So continuous position information smoothly. The sine and cosine wave create smooth periodic patterns that uniquely represent each noise level. So the periodic pattern uniquely represents each noise level. So this is better for the AI than just having each number represent noise level. Nearby noise levels 0.10 versus 0.11 produce similar but distinct embeddings, similar but distinct sine and cosine waves. While far apart noise levels look very different in the embedding space, in the sine and cosine space. This is important because the embedding is a continuous function. The model can interpolate between known noise levels. The model can extrapolate to noise levels it didn't see exactly during training, thanks to the smooth wave patterns. Why sine, cosine, not just numbers? Directly giving the noise scalar, for example 0.3 or 3, is hard for a model to interpret. Sinusoidal embeddings give the model a rich, high-dimensional signal with many frequency components. This helps the model disentangle the noise level information across many channels, improving learning and stability. Like how transformers use positional encoding for word positions. Sinusoidal encodings are standard in transformers for positions. Your noise level is like a position on the diffusion timeline. So the noise level is a position on the diffusion timeline. So this sine and cosine position embeddings are used in the original Attention is All You Need paper. So they didn't just use numbers, first token, second token, third. They actually used sine and cosine. Sines and cosine, yeah. So a smooth representation helps it generalize and generate better denoised outputs at every step. Then in the code, they have this embeddings variable and they concatenate sine values and cosine values over the last dimension. So this is the sine, this is the cosine, they just concatenate them. This is also why they use these sinusoidal functions in the original paper. So they provide a way for the model to easily learn about relative positions, and they can generalize to sequence length not seen during the training. Even just putting it as numbers, plus 1, 2, 512, this is a big number here, so we don't want these big numbers. We want to actually have like consistent scale of numbers, like between 0 and 1, the sine, etc. So now we understand the entire sinusoidal embeddings. You can also always ask ChatGPT to explain this more, and also I don't 100% understand it either. It's a bit tough, to be honest, like why exactly, what's happening exactly in the mathematics, why not something else? We should know all of that if we want to become like experts, but we will learn that over time, so don't worry. Next, we will understand these attention modules: multi-head attention, self-attention, cross-attention, MLP, the feed-forward layer, so that's not attention, that's just MLP after attention. These are used inside the transformer decoder block, the heart of the denoiser, so this is used for the denoising. So we are building UNet style decoder only transformer. This is confusing because I thought we are not building UNet, we are using transformer instead of UNet, but we'll see what this means. Where patches attend to each other, plus to label plus noise input. Let's see this now. We have this storage tensor 1, 2, 3, 4, 5, 6, 7, 8. And this is original shape 2, 4. So if I say rearrange x tensor x, and b is going to be the first dimension 2, and then the second dimension will be split into h and d. So basically this will do is split the second dimension 4 into h and d, and h will be 2. So then d will be 2 as well. So if I run this, 1, 2, 3, 4 is actually split into 1, 2, and 3, 4 now. If I say h is 1, then d will be 4. This is the inner dimension, and then h, the outer dimension, has just one element. If I say h is 4, then it will be 4. Yeah. So then d has one element. So that's what this rearrange does. Next, let's say we have tensor of shape 2, 5, and 12. So batch size, this is number of tokens in a sequence, for example, and heads, head dimension, and number of heads and dimension per each head. Let's say 12, or just let's say that we have this last number 12. So if you don't understand the attention mechanism, I explained it in my video coding DeepSeek from scratch. So you can just search for my search in the search bar and watch it. So I won't be explaining attention mechanism here too much, but basically here we have batch size, we want to rearrange. So n is going to be attached to this 5, and this will be attached to this 12. So we will split this 12 into h and d, and h is going to be 3, so d will then be 4. And then we will rearrange, we'll say batch, and then head number. You see, we put head here, so this is the 3. And then number, this n, this is the sequence length and dimension. So this is, we are splitting it by heads. So that's how it works. So the shape is now 2, 3, 5, 4. So let's check, it's this one, rearrange. So 4 in the middle, and then 5, 1, 2, 3, 4, 5, okay. And then these 3 are grouped, and then there is 2 of them, 2 big ones. So maybe this is a better way to visualize it. I'm just gonna create from 1 to 2 times 5 times 6, whatever the number is, 59. So the original and then reshaped. So it's based on this rule. So here age is 2, so we put 2 heads, and then what is n? A number of tokens, and then d is the dimension per each token. It's the same as what I just showed. So we will use that in our multi-head attention class. So it's very simple. Init super, we already know. We have some variables for heads. Is causal means future tokens are masked. Maybe future images, future tokens and stuff. Dropout level. This is for regularization. Number of heads. The forward pass. So for each of the query key value, we will just rearrange. Instead of having batch size, number of tokens, and the big dimension, now we will split into heads. And we will separate completely. So we put head dimension first. So we separate this. So then in each head we have number of tokens and dimension per token. So now they are completely separate heads. So we will assign that to query key value. Then we will calculate scale.product. If you don't know this, you can watch my video explaining Llama 4 from coding Llama 4 from scratch or DeepSeek from scratch. I explained this. I will not explain this now. So then rearrange, reshape back from batch size, number of heads, number of tokens, and then dimension to batch size, number of tokens, heads, time, dimension. So after we calculate the scale.product attention, we just reverse this process. So BS age and D to BSN, and then combine age and D. And age is number of heads. I'm not sure why I need to specify, because it should automatically infer shape of age. But anyways, and there is this self-attention class. So same stuff top here. And then we have this query key value linear layer, which is just going to be a linear layer from embedding dimension to 3 times embedding dimension, because we want to have a query key and value. And each of those will have embedding dimension. So if you don't know what embedding dimension, this is the vector embedding size. So I guess I expect you to know this attention mechanism. So you can watch these other videos here. You can ask ChatGPT. So multi-head attention, we just instantiate this multi-head attention class that we just created. So here in the forward, we will pass query key value here. So we are passing X. We are getting X, the tensor X, in the self-attention forward. And then we will extract query key and value by first passing X through our linear projection layer to project it into 3 times bigger size. And then we will chunk into 3 parts at the dimension 2. So this is the last dimension. This is the this X has batch size, number of tokens, and dimension, and the dimension embedding dimension. So let's explain maybe that line separately, this chunking and stuff. So we know that X shape is batch size, sequence length, embedding dimension. For example, it can be these numbers. So we have 2 images. Each image is broken into 4 patches. Each patch is embedded into 6-dimensional vector. And then this linear layer, this is a single linear layer that maps from embedding dimension to 3 times embedding dimension. It creates query key and value vectors in 1 pass. So this is same as language processing up until like in this attention mechanism, I mean. Why efficiency? It's faster to compute 1 matrix multiplication than 3 separate ones. If embedding dimension is 6, then input shape is batch size, number of heads 6, output shape is going to be same this but 18 here. So now this shape here is 3 times bigger. So what does this chunk 3 dim2 do? It splits the 18-dimensional vector into 3 6-dimensional chunks along dimension 2, the embedding dimension. So you get these 3. Now you have one tensor for query, key, and values. And why dimension 2? Because we want to split this last dimension here. Well, it's gonna be 18 after the linear layer here. So we want to split that dimension into 3. They call this feature or channel or embedding dimension. Now we can just remind ourselves how this computation of scale dot product self-attention works. So we have query, which is, let's say, this tensor. So let's say it has one batch, one patch. So one image, one patch. Sorry, this is one head. This is 2 patches, and every patch has 3 numbers in the 3 features, 3 channels. So manual attention, we need to get dimension of the Q vector and then to calculate score. So this is the classic attention. In attention is all you need. So we need to multiply queries and key transpose, but transpose these two. This is second to last and last. And then divide by square root of the dimension of this query or whatever. So square root of 3. Weight is going to be softmax over that, over the last dimension. And then output is just going to be multiply weights and values. This is the classic attention calculation formula. If I run it, we see here that we got some softmax. You see in softmax, each of them will add up to 1, each of these arrays. And this will also add up to 1. But we can replace all of that with this NN functional scale dot product attention. So that's the same idea, but this is optimized even more. I think they wrote CUDA kernels or Triton coders, so it works faster even. So by now we understand sinusoidal embeddings, multi-head attention, self-attention. So let's take a look at the cross-attention. You already know self-attention. Cross-attention is almost identical, except query comes from one input, for example, image patch, and key value comes from another, for example, label or noise embedding. So this text or the noise embedding. You'll need this to inject label and timestamp information into your image features. So we see this output is equal to multi-head attention, and the query is going to be image embedding, and key value will be label embedding. So this will help us combine labels, text, and image embeddings, images. So that's not written in this code here. This is just an example that will help us learn. So now we will understand the actual code. Surprisingly, it's the same thing. It's very simple. First, instead of calculating query, key, and value together, we just calculate query and key and value together. So from embedding dimension to 2 times embedding dimension instead of 3 times embedding dimension. That's the same thing. And later we just do the same split like before. And then query is separate. It will come from somewhere else. So we just have from embedding dimension to embedding dimension. This is because keep in mind that we will get the actual data, but the query vector should not be same as the embedding vector of the token or image or text. So it should be different. Query has different purpose than the token embedding itself. So that's why we need a transformation matrix. We need to transform. This matrix will learn how to transform the image embedding or text embedding into query, and it will learn what query needs. So that's why we need to transform actually. Other than that, it's same. Same as self-attention. Now let's look at this MLP layer and this MLP-SConv. So this is very simple. Just a sequential of linear, GALU, activation linear, and the dropout. And then forward will pass through all of this good stuff. So this MLP is defined here. That's the sequential list of these layers. So here we will have this expansion. So from embedding dimension, so after the attention mechanism, we get this vector that's juiced up with context, with attention from previous vectors, image patches, letters, tokens, whatever. So we need to expand to, usually these MLP multipliers can be 4, for example. So 4 times embedding dimension, then activation, then go back from 4x to just embedding dimension. So this middle layer, this 4x embedding dimension layer, that's gonna learn some useful how to transform this juiced up vector with attention. So it learns, it extracts, it understands this context that it got from other tokens, other vectors. So this is for processing the whatever we got after attention. I explained this also in my DeepSeek from scratch and Llama 4 from scratch videos. And then this MLP-SConv is using convolutions instead of these linear layers. Let's see how it works. So this is to introduce locality. First, 1 times 1 convolution is like linear layer. Then depth-wise convolution captures local structure, and another 1 times 1 convolution maps back to embedding size. Before we explain what all of that means and these layers more in details, let's see why to use MLP-SConv. Regular MLP sees each patch independently of the image. But I guess each patch is juiced up with the attention. So it sees, but it still sees it independently. But then this convolution adds local context via the depth-wise convolution. That's helpful in image tasks since nearby patches often relate. So it adds context from nearby patches, not just the single patch that it sees. So first, what is this conv2D, this convolution? You see, you have some image, you have this filter, this kernel. So it's gonna do some calculations based on these 3. So it will somehow, for each of these 3, it has some calculations and it will merge them into 1. So it will process these 3 with this filter or kernel and create the final number here. So this is to combine these pixel values. These are pixels, 9 pixels, to somehow combine them into this latent representation space. You can watch more videos if you don't know what the kernels and conv2D are. So conv2D takes in channels, out channels, and kernel size. This is the kernel size. Let's see this piece of code to understand it better. Let's say we got this image. So these are, let's say, some pixel values or something. And it has 5 rows, 5 columns. Okay. And then we will define some convolutions. So in channels 1, out channels 1, kernel size 3. So first of all, kernel size is for both width and height of the kernel. So kernel size 3 means 3 times 3 kernel. You can also specify kernel sizes 3,5 as a tuple to get height 3 and width 5. So let's see. In channels is how many separate layers, separate input layers the image has. For example, a grayscale image has 1 channel, just brightness. RGB image has 3 channels, red, green, blue. So channels in channel series 3 means each kernel filter will look at all three color layers. So I think that's understandable. Out channels. This is how many different filters you apply to the input. Each filter produces one feature map, one output layer. So out channel 16 means you are extracting 16 different features. So basically means you will have 16 different kernels with this kernel size. So each kernel will have some different numbers. And so each of the 16 kernels will transform these pixels on the image in some different way. Maybe it will make some edges sharper or maybe more blurred. So depending on how it transforms these numbers, we will get some different image. So you see here, if you have this image, we have this kernel going pixels left to right. This is what it can do. Maybe it will make all of the values 0 and then do like -1 here. And so you see how it's making how it's transforming these edges in detecting edges. So multiply this pixel, multiply this, and then add them together and put them into the middle place. So those 16 different kernels will be learned automatically during training in order to extract these features according to the training loss. So they get initialized randomly, and then there is this forward pass, loss computation, backward pass, update weights, the classic. So whatever the loss is, whatever you are trying to reconstruct or recreate or process, those weights, those kernels will be learned automatically. So let's say we just have one input feature, one output, so just one, no channels. Output, we just need to learn one kernel. And now we are going to just hard code our kernel instead of learning it. We want to see how it works. So it will say 1 times 1, 0 times 2, -1 times 3, and then same for this and same for this, and add them all up to get this -4. But you can see that we're going to lose outer edges because we are first calculating this whole 3 by 3 and putting the result into this middle part. And then this 3 by 3 into middle and 3 by 3 into middle. So we just actually have these middle parts. We're going to lose edges around. You can also, if you don't want to shrink the dimensions, you can add zeros all around. And then you will calculate like this part with zeros. So this is the formula. As I said, you just say 1 times 0, 2 times 1, 0 times plus, plus 4 times 1, and that's how it goes. This is how code example. We have 3 input channels, red, green, blue. Output channels is 2, so 2 kernels. Kernel size is 3 times 3. So it's a batch of 1, 3 channel 5x5 image. And then we pass that through this conv x. So output shape will be 2 filters, so 1 batch, so 2 filters, and 3 times 3. So the way it works is we have red, green, blue channels. Each channel has 5, we look at 5 times 5. Actually, the image is 5 times 5. So the first filter, we have 2 filter output features is 2. So it's not only going to look at the 3x3 square, it will also look at all of the channels. The filter will look at all 3 channels. So now it's 3x3 filter. And for the second filter as well. So each filter has 3x3 output in the end. So they will convert this 3x3 into a single number and then move and then number and then move and then number. And as I said, because it's 5x5, we will lose edges. So it will be 3 instead of 5 because we're losing edges, and 3 instead of 5 later. So this 3x3 is not from this, it's just in the end when we slide these through every single one, we get 3x3 output. It's not the same dimensions as these are different dimensions. So then this class uses these convolutional instead of these other linear layers to process more information, get more information from other patches as well, not just the current patch that it's processing. So main thing here is that classic MLP doesn't know pixel 1010 is next to 1011, so it doesn't take any data from this pixel. But MLP-SConv sees that and can act on it like CNN does, so it can know that pixels around. So scenario, pixels on edge of a cat's ear. What MLP sees, just color of the pixel. And what this other MLP-SConv sees is color and neighboring edge. Same for the texture in grass or sky. It doesn't just see the flat color of a single pixel, it also sees neighboring patterns. So this MLP-SConv is gonna look at the nearby patches, 3x3 neighborhood of patches, while just MLP will just look at the single patch. Then if we look at decoder block, this will just unify self-attention, cross-attention, MLP class, all of it. And we have some layer normalizations. So self-attention will pass input X through normalization and residual connection after the self-attention. Same for cross-attention, but in cross-attention we will do X input and Y. So Y, we can see here, Y is noise label embedding. So noise level, we're gonna get the noise level. This is the frequencies, our sine curve, and the label, the text label. So the sine curve saying how much noise, the noise timestamp, and the text embedding, and we will do cross-attention with that. And MLP, we also have a residual here, and then MLP through normalized X, you always need to normalize, and residual, and that's it. That's the whole decoder block. So then here in the denoiser pi, we have denoiser transformer block. So let's see. We have a bunch of these hyperparameters, patch size, image size, channels, and etc. So let's analyze this. It processes a noisy latent image, like a scrambled 32 times 32 image, for example, and denoises it conditioned on label and timestamp information. That's why in the cross-attention, it's using a stack of transformer decoder blocks that do self-attention over patches, cross-attention to guidance, so label and noise level embedding, then run MLP like processing via MLP-SConv. So it starts with these hyperparameters. So first this patchify and embed. It's NN sequential. It has conv 2D. It has this rearrange to flatten into sequence of patches. So you see here batch size and then D here, and age W will just be grouped. So it's a sequence, it's flattening. Now it's not 2 dimensions, but just 1 dimension flat. Layer normalization, and then linear layer from patch size to embedding dimension, patch dimension. So this will just convert each patch into embedded vector, into feature vector. And then normalization for that embedding dimension. Normalizations are often needed. So this linear will project each patch to embedding dimension. So this takes an image of shape B for 3232, so batch size, 4 channels. This is a bit weird, so I guess it has also alpha channels, so red, green, blue, alpha, I'm guessing. So cuts it into 4 times 4 patches for patch size 4, flattens them into a sequence of patch vectors, projects each patch into an embedding. So the output shape is number of patches, batch size, number of patches, embedding dimension. So it could be 64 if it's 8 times 8 in patches. And 256 could be embedding dimension for each patch. Then we have this positional embedding. So it's going to be learnable embeddings. So it's going to be sequence length and embedding dimension. So for each patch, there is this embedding vector. It's going to encode position, and it's learnable. We also have some pre-computed positional encodings, so I'm not sure if we use them together or separately. We choose one, we'll see further. So this is just pre-computed. It goes from 0 to sequence length. So I guess 0, 1, 2, 3, 4 until sequence length. So we get that array here, and we just save it as this variable. And then this would be not learnable. This variable is learnable, this variable is not learnable because this is register buffer and this is an embedding. We will see further if they are used together or separately or how. So then we just stack a bunch of decoder blocks based on this hyperparameter number of layers. So we have NN module list and inside decoder block this amount of times. And you see here that in the decoder block, so it's a list, but we pass in all of these hyperparameters and instances, embedding dimension, MLP multiplier, this MLP-SConv class, etc. And in the end, we have this owl projection. It's just a sequential, and then sequential again, a list of linear layer from embedding dimension to patch dimension, and this self-rearrange 2, which we need to look into. So it's this one. I skipped that, so let me explain that. So this linear in the output projection, reverse of the earlier projection, so it projects from embedding dimension to patch dimension, and self-rearrange 2, this is gonna turn that back to the image. So the goal of this rearrange 2 is, after processing patch embeddings through the transformer, we want to reconstruct the image from the patches. So the input shape before rearranging, let's say we have image size 32, patch size 4, so this is pixels, 4 pixels per batch size. Then number of patches along height and width is 8, because so now it's height times width is 64 patches, because we divide 32 pixels by 4 pixels, so we group, so each patch has 8 pixels. Oh, no, sorry, each batch has 4 pixels and there is 8 patches in total. So assume C is 4, these are latent channels. So this is the embedding dimension. So then your tensor will look like this. Batch, that's whatever number of images, and then number of patches, 64, and then patch dimension. That will be 4 height, 4 width, and 4 channels. Yeah. So we have batch size, number of patches, height, width is just number of patches, not the pixels. And then channels is 4, so red, green, blue, alpha, for example. And then patch dimension and patch dimension, width and height of the patch in pixels. We want to rearrange that, so we get batch and then red, green, blue, alpha, so 4 separate images, 4 separate channels, and then height times number, so number of patches times number of pixels in each patch, and width as well. So we arrange that back to the image. So this is an example. We have 1, 64, 64. So as I said, we have 1 and 64 is the number of patches, yeah, and we will divide. We put it into brackets here with rearrange, so we divide that into 8 and 8. And 64 here, this is a flattened image, so number of channels, height and width, but we divide this 64 into these 3 as well. And so when we divide this into these numbers, we need to specify the dimensions. So the height here, it's going to be image size over patch size, so it's going to be 8 if it's, yeah. And then P, so then this width can be inferred, so P we need to define as patch size, and P2 is patch size, and then C can be inferred, whatever dimension remains. So that will be it for this init part. Now let's check the forward. That's a lot shorter. So the forward, before we look at the code of the forward, let's see what it does on a high level. First, this first line will convert into patches and project each patch into embeddings, as I explained. So it's patchify and embed. Then we need to add positional embeddings. So we have this positional. So here we take input and say input plus self positional embed, positional encode. So let's see this positional embed. We defined that. So let's see how this positional stuff works. As I said before, we define this learnable layer, which is with embeddings, and we define this static variable, pre-computed positional encodings. So here we create this positional encoding variable, and then we just add that, pass that through the positional embed, and then add it to X. So what does this even do? Let's see now. Let's explain that code. So we start with this positional embedding and an embedding sequence length and embedding dimension. So sequence length is the total number of patch tokens, 64 if you have an 8 × 8 patch grid. Embedding dimension, size of each token vector, 128, 256, etc. So this creates a lookup table of shape, sequence length, embedding dimension. So lookup table, there are vector embeddings for each number in the sequence. So if there is 64 patches in the image and the embedding dimension is 128, this embedding matrix will have a shape 64, 128. And then let's see this line by line code. You are saving a list of token positions 0 to 63, 1 per patch. So when we are doing a range from 0 from sequence length, we already knew that. This is not learnable since it's a buffer, just stores so we can look it up. And then positional encoding. So now we have this more complex line. We see pre-computed positional encodings, and then we see we're taking some of it. Let's see what we do here. So let's suppose X shape is batch, sequence length 64, and embedding dimension 128. So these are the tokens, the X, the input. So pre-computed positional encoding from 0 to 63. So positional encoding shape is 264. Same batch, same position IDs repeated. So we have this initial pre-computed vector 0 to 63, and that's just for one image. So depending on the batch size, depending on number of images, we want to just multiply that for every image. So we have one for every image. So we have this, we take everything, the whole vector from beginning to the end. So the x size is going to be 64 in this case. So x0 is the batch size. x1 is going to be the sequence length of the x. So the second dimension is x is sequence length. So it's going to be 64, whatever. We take all of this entire vector then, because the sequence length is going to be equal to the size of this vector. But even if this vector is longer, then we will just take the number corresponding to the sequence length of the x, because we don't need any more of the vector positional embeddings for, yeah. And then we do this expand. We see expand. So this expand will just copy this guy, but it will pretend, it will not actually copy in memory. It will just pretend to copy. It will, okay, we'll see what it does. So expand, so it's gonna create the same batch dimension. So if there was 2 batches, it will just multiply it 2 times. And this means keep the same size as the original along that dimension. So I guess -1 is the last dimension. So if this has this dimension 64, then x size 0 is 2. Also, yeah, it results in 2 and 64. So that's how this positional encoding is just creating encodings for every image in the batch. So batch number of encodings. And then we pass those positional encodings through this positional embed layer. So what does this do when we pass this through this layer? So this performs a lookup. You know, this pos.emb is a lookup table, as I just explained. It has 64 positions, and for each position there is embedding vector that's learnable, which will tell the AI about that position, what it should do. It will tell AI will know which position it is when it sees this vector. So this performs a lookup when you pass this. So position embedding is position embedding, self-position embedding of this position encoding, which returns. So shape of this new variable is going to be batch size, sequence length, embedding dimension. So for each image, for each token in the sequence length, it will give entire embedding dimension. So for each sequence length, for each image, for each patch, for each image, it will just give this embedding dimension for that particular position. And those embeddings will be learned. That's NN embedding. For each token or patch, the embedding corresponding to its position is retrieved. And that's it. So then we add those embeddings to the X. It's just adding with a basic plus. So they are added element-wise. So you see that every number in the embedding will have corresponding position number. So they will just be added element-wise like this. Now let's see this denoiser class. We have image size, noise embed dimensions, patch size, embedded dimension dropout. So a bunch of stuff here. We just assign those variables. And then we have this Fourier features. So that's a sequential layer. So it takes a scalar noise level like T, so like 0.8 or 0.3, and uses sinusoidal embeddings that we just created earlier in the video, and makes it a rich vector using many sine cosine waves. So the embedding, you remember, projects it into the same dimension as image tokens, so we can combine later. So this is what we already have. And then we project noise embedding dimension into embedding dimension of the image patches, GALU, and then again, final projection. Maybe this will also learn something. We have this middle layer. so that will learn something. Now your model understands noise level not as a raw number but a feature vector. Then we initialize this DenoiseTransformer block and normalization and label projection. So normalization layer and then linear layer that has text embed size to embed dimension. So label projection maps clip text embedding 768 into same size as token embedding, so the patch embeddings. And then norm normalizes the final noise plus label embeddings before passing into the transformer. So let's see what forward method does. It gets X, the patches, noise level, so just the timestamp and the label. So we already know this stuff. Clip encoded text prompt for each image. Shape is batch size 768 because this is the text embedding vector. So we first generate the noise and we unsqueeze first dimension to add here the first dimension. Turns scalar noise into learnable vectors. Unsqueeze one, adds a dimension, so shape becomes this, as I just said. I think we will, because we will add this to the sequence, but we don't need a sequence length here because it's going to be same for the entire sequence. For the entire sequence of patches, it will be the same noise level because it's same noise level for the entire image. The label, we will also unsqueeze the label to have this sequence length because we will add it to the entire image as well. And then we just concatenate them alongside first dimension. So now we will have number 2 here. So we will basically group them together. And that's it. We will just have noise embedding and label embedding next to each other for each batch, just grouping them together. So that's it. I think now we understand this denoiser as well. So it will just return X after it has processed, after it has done this forward pass. So that was it. We have a very long ChatGPT conversation here. I'm gonna leave it to you so you can take a look yourself as well. And I'm gonna leave this the Google Colab in the description below. So now we have the core understanding of diffusion transformers, and you can go to my channel and check my other videos here. And we may be training diffusion transformer in the future, most likely. So subscribe and thank you for watching. See you next time.